Welcome to signal processing for millimeter wave communications for 5G and beyond. So, we will be continuing the millimeter wave channel model with RX beamforming first, and that is the continuation. And we will be covering some of the approximations involved that we have already started in the last class, and we will continue for the characterization with the multiple channel. So, this is where we left it. If you look at the diagrams, so this is where we left it. So, we said that if we are in a far field and if the distance between the antennas are very small, which is the case for millimeter wave, we can make such assumptions. Now, is this assumption true for even sub-6 gigahertz? Of course, true, because I have not said that this is only applicable for millimeter wave. The only thing that has been said is that the dimension of the distance and the order of the distance and the distance between the antennas. What is the relationship? If you look at this is 2.5 millimeter for a 60 gigahertz and I am assuming 1 meter. If it is a 6 gigahertz, what would have happened? This probably would have been even larger, and then I have to consider even a larger distance. That is all. Suppose I assume a 1 kilometer distance or a 2 kilometer distance in that case. And then even if the antenna separation is 1 feet or 10 meter, not 10 meter, 10 centimeter, probably I would have taken the same approximation. Okay, so this is a general approximation. So it is the order of the distance and the order of the antenna spacing. Okay. So now let us get into the. Okay, so this was the last assumption that all the distances have to be almost equal. Okay. So, now each di whatever the distance is will be almost same with respect to Rx antenna. So, that means d1 almost equal to d2 and so on dn if lambda is very small with respect to each di. So, that we have explained it. Let us see. Okay. Let us see what are the other assumptions. So, distance is same. Does it mean that HI is same? I am talking of the channel, because distance is one contributor for the channel. What does it contribute to? Distance, because based on distance you have path loss, based on distance you have a phase, all these things will come into picture. So, when I say my distance is equal, does it mean that the channel itself will be equal? Okay. Let us understand that. Okay. So, then the channel HI, the channel gain, that may not be equal. So, and why that is different when my distance is still same? So, can I create some sort of what exactly creates the inequality? Okay. That we need to understand that. Now, from a channel point of view, what are the components that I am in a ADC mode? That means I am completely a single tap channel. So, I can think of this just like a complex number. So, this is say D1, D2, I will say my channel is say H1, H2. Distance is almost equal, but let us see the channel part. Now, when it is a H1 and H2, it will be a complex number, because I probably viewing it from the ADC point of view, after the ADC, from the digital point of view. So, my H1 and H2 is a complex number. So, that means each HI, I would say, if it is a complex number, what does it mean? Some gain will be there and some phase term will be there. I can think of, right? That's the quite general assumption here. Alpha I to the power j phi I for every HI. What is alpha I? Alpha is your the actual path loss gain or absorptions gain, everything is there. Now, I am not making any discrimination that it should be only path loss, it can have everything, because we are dealing with millimeter wave, everything. So, alpha I is everything. So, it is a gain coming from frisch, that is the pure path loss, it is a gain coming from absorptions, it is a gain coming from different phenomena like reflectative, everything is same. Now, in this particular case, we are not assuming any phenomena, right, like we are assuming no reflector and scatterer. So, probably this may not appear, but at least these two will appear in a millimeter wave context, there is no difference. Okay. So, this alpha will have that. Okay. Now, here the question comes, will the alpha I be different for different path? Because if you look at Frisch, what does it depends on? It depends on distance d. What does the absorption depend on? Of course, once the frequency component, at the same time it will also depends on I. So, if you look at alpha, it was e to the power minus half into k into f into r, or rather d I would say, in this case d I distances. So, kf is your absorption coefficient. So, it is dependent on di, and you know the Frisch part. Okay, it will be root over of dt dr lambda by 4 pi di. So, di is compulsory everywhere. Okay. Now, we have assumed what? Di is same, almost same, right? Every di is same. So, which means that apart from anything else, that means apart from di, the other components are assumed to be same. That means I am assuming a frequency, I am talking of the same frequency here. So, these are frequency dependency. If I do not bring the frequency dependency, there is a frequency of course, but if I do not consider my bandwidth to be very large, I would say my that part is taken care. So, it is a distance that matters. Now, if the distance is equal, this part is equal, this part is also equal. That is the consequence. What does it mean? That means, because I have assumed the distance to be almost equal, my alpha 1, alpha 2 dot 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 alpha, if there are n paths, they will be equal, almost. I should not say they are equal, they are. That is an approximation, key approximation. So, which means that I have assumed there the magnitude part of the channel is constant for all the paths, and that is a very critical assumptions. So, this was not the case when we considered the 6 gigahertz channel model, right. This is also 6 gigahertz, I mean you can equally apply the whole thing here as well. We are not deviating from what we have learned, it is just an approximation. Now, you are saying that hey, we have a channel vector h1 to hn, but the magnitude part of the channel is actually almost equal, because the path is almost equal. Now, that part is taken care. What about the phase part? Will the phase be same? Because you can always say, hey, what is phase? Phase is nothing but what is phase? So, what does the phase depend on? Phase depends on your distance, right? Phase depends on your distance. Now, if the distance is equal, won't the phase be same? Natural questions, right? Now, here we are making a small distinction. We are saying that no, phase depends on your distance definitely, but it also depends on your lambda. So, that means if the distance between 2 points is lambda apart, I will not feel any phase difference. Suppose I have a point here, I have another point. Suppose I am making a transmission like this, and there is a receptor data here, and there is another antenna sitting lambda apart. Will I see a phase difference? Suppose this is 100 meter, but from here this is just lambda is equal to say 1 millimeter. It is a tiny. Will I see a phase difference? I will not see a phase difference. Suppose this is lambda by 4, even tinier. Will I see a phase difference? Yes, now I see a phase difference. So, it is not the distance that matters. Obviously, distance finally comes into the picture, but it is with respect to the lambda, how much fraction. See, if I divide this d by lambda, so there is an integer part and there is a fractional part. So, it is this fraction that determines how the phase is, not this integer. So, this d is actually material to some extent. It is this fraction that matters. And what is this fraction? If this lambda is say 5 millimeter, That means a distance between 0 to 5 millimeter will create a phase difference. If the distance difference of some two objects is just say 1 millimeter, I will say phase difference. Will I see alpha difference, the gain difference? No, I will not see alpha difference, because 1 millimeter is nothing almost, right. But this phase is sensitive to that fractional part, not this integer part. That is the reason, even if the d is same, almost same, I have not said equal, it is almost same. So, that tiny difference is good enough. So, that means this d 1 is almost equal to d 2, it is not equal. Why it is not equal? It cannot be, because there are these are two different physical points, it need not be same, it can be different. But this almost same is good enough for making the gain part same. But this is not good enough to make the phase part same, because phase depends on the d by lambda's fractional part, not the integer part. So, which means even if the d is 10 kilometer and lambda is just say 5 millimeter, a 5 millimeter difference is good enough to create a phase change, but that will not be reflected in your alpha, and that is the key part in this millimeter wave. So, in a summary, if I say this channel from 1 Tx to every Rx, alpha is same for all of them, which I comfortably can assume, but this phi will not be same for all of them, because this phi is Helen-Evan difference. In fact, it can even be a negative phase difference based on the distance, and that can be a very tiny difference. And this is the key point that I am trying to say here. Okay. So, that means if you look at the fourth point here, this one, fourth point here, each hi can be expressed as hi equal to alpha into to the power j phi, where alpha is almost same for all, but this phi, the next point, is basically the phase, and that is basically your different part. And if you look at this diagram, which will make the point clear. Okay. So, before I go to the next diagram, so this is the key assumption here. So, this phi is basically your phase differences. Okay. So, what is the consequence of it? Okay. So, consequence is that I have taps, single tap having the same magnitude, but different phase, that is all, that is the consequence, correct now, because if hi is equal to alpha into e to the power j phi, this one hi is equal to alpha I am not putting alpha I here, because alpha is now same for all of them, almost, the tiny difference is not an issue, but this phase will be different for all of them. Okay. So, this is a very key difference. This is a good approximation. Okay. So, this is my first good approximation, or the consequence of assuming my distances being same. Okay. So, what is the next approximation? What is the next approximation that comes into our picture? Okay. Next approximation that comes to our picture is the angle of arrival. Okay. So, what was the angle of arrival? Angle of arrival is nothing but at which angle the ray is incident on a particular antenna. And what are the two components for an angle of arrival? It will have two components of elevation and azimuth, both will be there. Okay. So, that is the point here. Now, for our simplicity, we are just taking one angle for our case, because this is kind of a uniform linear array. So, one angle is good enough, but if you take UPA, probably elevation and azimuth both will come into picture. So, here we assume that my probably my azimuth angle is same for all of them. So, that is what happens. So, when you have a ULA, the way the beam is done is that you can play with the elevation angle, not with the azimuth angle. So, the steering that I was talking of, you can play with only the azimuth angle, elevation angle. So, if it has a by default azimuth angle, you have to live with it. If it has a elevation angle, you can play with the elevation angle, provided the antennas are in ULA position. But if it is an UPA position, you can play with elevation angle and azimuth angle. We will explain that later, because this is not part of that context, but I am just telling you this is what is going to happen. So, when I am in a ULA configuration, meaning my antennas are in a Z direction, simple Z directions, x, y, z. If you have, you can just think of say x, y and z, and you are just thinking of z direction. So, you can say that the only steering you can do is in the elevation part. That means only one direction you can shift, but not in the azimuth part. So, let us assume that part, and then we will extend it. When you go for UPA, you will see that you can this angle of arrival will have, anyway angle of arrival will have both the component elevation and azimuth, but here I am putting elevation because that is the only component I can change it. Azimuth is fixed for us. So, now what happens to my angle of arrival? Okay. This is another approximation. So, first approximation distance, and we have seen its consequence. What is the second approximation? Second approximation, look at the first diagram here, the first one here. So, these are the two antennas, received antennas. So, if they are slightly spaced apart, no matter how small, obviously the ray that will be falling on them will also have two different angle of falling, because the source is a point source, right. So, if you think of from here, so this is a point source, I am assuming, right, probably this is a point source. So, the rays are like going all direction, because this is a isotropic ray, I am just assuming that. So, even if you have one more antenna here and another antenna somewhere here, so this will never have the same angle of arrival, though there is a distance, if there is a distance, and this will have some distance, right. Now, this angle of arrival, so this is what our point was, theta 1, and this angle of arrival was say theta 2 with respect to horizontal. Okay. So, now go back to our diagram. Will this theta 1 and theta 2 be really different if the distance between Tx and Rx is assumed to be large enough compared to the distance between the two antenna? Okay. So, that is the point. So, that means if I say I am in a far field, what does it mean? My Tx to Rx antenna is in the order of say few meters compared to the distance between two antennas, which is in the order of millimeter. If that is what the dimension, then it is as if like both the antennas will see that they are receiving the ray in a parallel fashion, just the way we see the sun. If I see the sun the way I am seeing it, 100-meter away also another person will see the same way it is as if like both of us see the sun in a parallel manner. We will not see any inclination difference or angle of arrival differences, because the distance between sun and earth is so large, that difference will. But if somebody is standing on earth and somebody is standing on say Jupiter, yes, the angle of arrival will be different, because the distance between Jupiter and earth is also of the same order. But on earth's surface just 100-meter away, I will not see that angle of arrival difference. So, this is precisely another approximation. Of course, it comes from the same approximation of far field, the distances are almost same. So, here also in the second approximation of millimeter wave, which is the angle of arrival estimation, that each and every antenna is receiving the rays in a parallel manner. That means, their angle of arrival or angle of actual incidence of arrival is same for all of them. Instead of theta 1 and theta 2, now it becomes theta for all of them. Okay. So, this is another approximation. Okay. So, let us see what are the other. So, what are the two approximations that we have learned? One approximation is that every channel tap has equal gain, because the distance is out to be almost same, but the phase is different. Then each and every antenna will see the parallel rays coming, as if it is not a two different antenna will see two different angle of arrival, because the distance is again assumed to be far large compared to the spacing among the antennas. Okay. So, the angle of arrival remains again the same. So, these are the two assumptions we have learned. Let us see what is the consequences that these various phi and all these things will have it. Okay. Okay. So, let us see that. So, so what does it mean? Distance is same, phase is different. Now, if the phase is different, what should I do? We should now say somewhere in our equation this difference of phase should be evaluated, right, because we know phase will be different. So, can I evaluate it? Well, so for the evaluation purpose, I bring the second point here. Why the phase is different? Because di and di plus 1, if the distance, the ith path and the I plus 1 path distance are not same, they are slightly different, and that slightly difference itself is good enough for our phase. So, when I do a phase estimation, that means if I want to estimate how much my phase would be, at that time I would say these two distances are not equal. So, that means this is the second point comes into picture. So, let us assume that the difference between two consecutive incoming rays, that is the ith path and I plus 1 path, is delta I. So, this is what this part, the second part. So, let us assume that this di minus di plus 1 is delta I is equal to 1 to n minus 1. So, it is the two consecutive path has a small difference of delta I. Okay. Now, this is consecutive difference. Now, let us go back to our again some of the discussion. So, what does it mean? It says that I have a, this is my antenna here, this is my another antenna here. I have another antenna. Let me just magnify the distances and spacing for our own discussion. So, let us assume this part is this part. So, let us say this is my di, this is di plus 1 consecutive, mind it, and there will be one more antenna. Let us assume there is one more antenna here. So, this should be my di plus 2. Okay. Let us assume this is the first antenna, this is the second antenna, and this is the third antenna, and they are just linearly placed, and this is my frame of reference. That means I am standing there, and from there everything is looked at. Let us assume that di is the smallest one among all of them. That is maybe the smallest one. It is not a big deal to assume it for simplicity. So, let us assume this di is the smaller compared to everybody. So, the first antenna among these three, let us assume this. This is easy. I mean, without hampering the generality aspect, this you can safely assume. The first one you can assume is the smallest one, and as you go down to the antenna, the distance is increased. What does it mean? It means that if I draw a circle from this point to this point, take that as a radius, and I draw a circle. So, what will I get? I create a circle, right. So, it is like as if like I am drawing a circle from this point with a radius of di. I will cover, I will cut like that, right, if all of them are greater. So, that means as I move along my antenna positions, I will see this distances increases. So, this is the first point, then there is a second point and third point, and this is what. So, that means can I make a small point here, till here or till here, the phase will be equal. Why? Because the distances are exactly same for all of them, but from here to here the phase difference is caused because of the small tiny difference in the distance, because of this small tiny difference in the phase, in the distance. So, that small tiny creates the problem for the phase 1. Okay. Now, what we have assumed here in this particular context, that this one, let us assume this one is the delta I. Let us assume this is the first one, this is the second one, or let us say this is delta 1. This can be assumed to be delta 2 and so forth, right. And you can predominantly see that for this configuration delta 1 must be greater than delta 2 must be greater than delta 3 and so forth. So, this is how the configuration is, and these deltas are responsible for the phase differences. This is what our assumption is. Now, we will do some sort of a geometry and some trigonometry and try to see how again one more level of approximation can lead to another interesting result. Okay. Now, because now this delta 1 and delta 2 are not known to us. Why it is not known to us? Because I do not know the distance between them, between each and every antenna to the Tx, that is not known to us. The only thing we know that they are, whatever the distance is, it is almost equal, that is the only difference we know. And this delta 1, this di is so large, even if I draw a circle, this small delta 1, that means this small delta I is very less than any of the d you can take it, very less. I mean, that is obviously right. It cannot be large enough, because this distance itself is very small, that is a small tiny lambda, like a 2 millimeter, 3 millimeter. So, how much this difference? They will also be in the order of millimeter only, they will not be very large, because this distance, this di itself is a very large distance, maybe in the order of say 20 meter compared to say millimeter. Okay. So, this delta is like a small millimeter dimension compared to di. So, I can safely assume. Now, what does it translate to our phase? Does it give us an advantage? Okay, that we need to understand. Secondly, I still do not know what is delta I, this I do not know. Can I make some approximation? Okay, and that is precisely our next level of approximation, that how exactly the phi, because this delta I determines what? This delta I drives my phi finally, that drives my phi, that difference, because of this delta I get a difference in my phi, very straightforward. Okay. Now, the question is that I do not know. So, can I do one more level of approximation by which I can guess what my delta I should be. Okay. Now, with this I stop the class today. So, in the next subsequent class we will be talking of the generation of this phi, how I can make that phi determined. So, what are the three assumptions that we have made so far? One is the distance to be equal, then channel, that makes the channel gain to be equal, then the phase we have not made it equal, because that is the key point. And third one, what is the third approximation? AOA, angle of arrival. We have said angle of arrival is also equal for all of them if it comes from the same source. Okay. That means Tx, no reflector or scatterer, when it reaches to the all antennas, the angle of arrival is same. So, these three approximations we have. The next level of approximation is delta I, the difference between the distances. Okay. Conclude our session today. So, we have learned some more approximations, predominantly AOA and the distance things again, and in the next class we will be phi or the angle differences, how exactly they prop up in our discussion. That's it. Thank you.